तेजस्विनावधीतमस्तु मा विद्विषावहै। ॐ शान्ति शान्ति शान्तिः।
In the last class we had started our discussion on MESFET based logic circuits, and we had discussed two logic families, that is the direct coupled FET logic and the super buffer FET logic, both of which use a combination of enhancement mode and depletion mode transistors. Now it is sometimes difficult to fabricate both enhancement mode and depletion mode transistors in the same wafer. I mean, you require a more complicated technology for that, and also enhancement mode devices are more difficult to fabricate. It requires a higher degree of accuracy in all the technological processes. So there are other logic circuits which use only depletion mode transistors, and they are technologically more easier to fabricate, and that is why they are quite popular also. So we shall, in today's class, we shall take up two such logic families, okay, which use only depletion mode transistors. So like as always, we shall start with the inverter, okay. And in this case, since we are using only depletion mode transistors, we have two depletion mode MESFETs. So this is the driver transistor and this is the load transistor, and for the load transistor the gate to source is shorted, okay. And so VGS is equal to 0, and by adjusting the VDD we can again ensure that the load transistor is always in the saturation region, okay. Now this circuit has a certain problem. Suppose this has to drive another similar inverter. Now if you are driving a similar inverter, okay, what is going to happen is, since this voltage here at the output of this gate is always going to be positive, okay, because there is no way this voltage can go negative, okay. So the input voltage to this to the next stage inverter is always going to be positive. Now since this is a depletion mode device, okay, in order to turn this transistor off, we require to have a negative voltage at the input. So this output voltage, since it does not go to negative values, it is unable to turn off the input transistor of the next stage. So that is the problem. So how do you solve the problem? The way to solve the problem is to use a level shifting arrangement. To do that, what we use is, we use two diodes which are used as level shifters, and what we have what is called a pull down transistor, okay, which is again a depletion mode device with the gate to source shorted, and here we have a negative supply voltage minus VSS, okay. So this voltage here, so a current will always flow in this through this pull down device, we call the pull down device, okay. And what is going to happen because of this drop across the diodes, so this voltage here is going to be level shifted by two diode drops. So if we call this output voltage VO prime, say this actual output voltage here is going to be VO, and VO is always going to be VO prime minus twice, we can call it V gamma, where V gamma is actually the cut-in voltage of the diodes. So there is going to be a level shift between these two devices. Now suppose this voltage can be positive, but the V output can now go negative. Now this output voltage is going to be fed as input to the next inverter here. So, we have, so this is the input stage of the next inverter. So, the basic circuit for this logic family is going to be this, okay, where we have an inverter followed by a level shifter. Now, how to find out the input output characteristics of this inverter? Okay, again we follow the same procedure, that is we can do it graphically by drawing the output characteristics of the driver device. Okay. So, we draw ID VDS for the driver device, okay, and then what we have to do is to draw the load line, okay, as usual, to find out the input output characteristics. Okay. Now, let this be the characteristics of the driver transistor. Okay. Now, before we go ahead, let us now fix certain values for this device. Okay. Now, let us put VDD is equal to 3 volts, let minus VSS is equal to minus 2 volts. Okay. So, you have a plus 3 volt power supply, you have a minus 2 volt power supply. So, all these circuits using only depletion mode devices must have a dual power supply, that is a positive power supply and a negative power supply. Okay. So, you have VDD minus VSS. Now, as we have already said that the length of the channel length of each transistor is always maintained at the minimum value. So, we have the driver transistor length is equal to the length of the width length of the load transistor and is equal to the length of the pull down transistor. But the width of the transistors will be adjusted. Now, suppose we have the length of the the width of the driver transistor is equal to the width of the load transistor is equal to the twice the width of the pull down transistor, which means that the pull down transistor has half the width of the driver and load transistors. So, in all other respects all these depletion mode transistors in the circuit are identical except the widths of the transistors. Okay. Now, let the threshold voltage of these transistors be minus 0.9 volts. Okay. All right, and we have and let V gamma, that is the cut in voltage, be 0.7 volts. Okay. So, now in this characteristic, since the threshold voltage is minus 0.9, you can put minus 0.8, minus 0.6, say minus 0.4, minus 0.2, 0, plus 2, like that. Okay. These are the gate to source voltages. Okay. These are the gate to source voltages for which these are the characteristics. Now, how do we draw the load line for this structure? Now, normally what we do is we draw the characteristics of the load device, okay, starting from VDD here and inverting it along the x axis. Okay. But here what is small difference is there, that you see because of this pull down structure, okay, a level shifting structure, a current is constantly going to flow through these devices. So, for this we have the load current, the current of the load transistor is equal to the current of the driver transistor plus the pull down current. All right. So, the load current is equal to driver current plus the pull down current, which means effectively that ID is equal to IL minus IPD. Okay. ID is equal to IL minus IPD, that is the driver current is equal to load current minus the pull down current, okay, which means that the driver current is not equal to the pull down current, and this must be taken into account while drawing the load line. Now, suppose let us take that this is equal to 1 milliampere, let us say, all right. That is when VGS is equal to 0, okay, the current flowing through the device is approximately 1 milliampere. Okay. And so, for the pull down device everything is identical except the width of the device is half. So, for the pull down device, when the gate to source voltage is 0, the current flowing through it would be half of this current. Okay, that is, you have half a milliamp, 0.5 milliampere would be the pull down current. So, if you now look at this expression, so ID will be IL minus the pull down current, which is 0.5 milliampere. So, to draw the characteristics, okay, what we have to do is we have to shift it down by 0.5 milliampere. So, if this is say 0.5 milliampere, okay, now we have to take the VDD, that is, this is say 3 volts, okay, and draw the characteristics, okay, from here, all right. So, this is the origin, and so the load characteristics would be something like this. Okay. So, this is the characteristics of the load device. This is shifted down by 0.5 milliampere, which is the current flowing through the pull down device. And now the intersection of these two this set of characteristics for the driver device and this characteristic for the load device is going to give us the operating point. There is another constraint here, that since the input voltage here cannot rise above 0.7 volts, that is, the output voltage of this inverter here cannot rise above 0.7 volts, because it is going to be clamped by the input Schottky diode of this MESFET, depletion mode MESFET. So, this is maximum value is 0.7 volts, here the output voltage, the maximum value is going to be 2.1 volts because of the 2 further diode drops. So, we draw also the characteristics of the diode here. Okay. So, if this is 2 volts, okay, this can be 1 volt, this is 3 volts. Okay. So, 1.5, 0.5 say, this is 2.5 and so on and so forth. So, this is the characteristics of the 3 diodes together. So, the output voltage cannot exceed this value. So, the output voltage is also always going to be limited by this value here. Okay. Now, so now after having drawn this, okay, we can now find out the input output characteristics. Now, let us see, when the input voltage, let us put in Vi, Vo prime is the output voltage of this point, at this point here, that is of this 2 transistor section, that is before the level shifter, and Vo is the actual output voltage, which is shifted by 1.4 volts. Okay. So, now if Vi is less than the threshold voltage of the input of the transistor here, say it is say minus 1 volt. Okay. So, this current is 0. Okay. Now, this voltage here, so the point of intersection is here, but since the output voltage cannot exceed this, Vo prime is going to be 2.1 volts, okay, 3 diode drops, and this one is going to be 1.4 volts less. Now, if you take minus 0.8 volts, okay, it is still the point of intersection is here, which is beyond this point. So, again we take it as 2.1 volts, which is 0.7 volts here. If it is minus 0.6, again the point of intersection is going to be here, which is beyond this curve. Okay. So, again if it is minus 0.6, 2.1, 0.7. Okay. Now, if we go to minus 0.4, let us see, this is minus 0.4 curve. Okay. The point of intersection is here, okay, which is on this side of this curve, okay. So, the output voltage is going to be, okay, almost equal to 2 volts, say 1.9 volts. If it is 1.9 volts, so the output voltage actually falls to 0.5 volts here. Again, if we take the curve, next curve, that is minus 0.2 volts, okay, we find that the output voltage has dropped significantly. The point of intersection is now here, okay. So, which may be minus, for minus 0.2 volts, the point of this is going to be around 0.4 volts. So, this output voltage is now going to be minus 1.4, then it is going to be minus 1 volt, 0.4 minus 1.4 minus 1 volt. Okay. Now, if you go on increasing this voltage, say 0, the point moves to this. So, you have 0.2 minus 1.2 and so on. Okay. If you go to plus 2, it will be 0.1 minus 1.3. so on. So, what we find is that from this characteristics here, all right, that when the input voltage exceeds as the input voltage is increasing from -1 volt to 0.2 volts, okay, the output voltage initially is at 0.7 volts, which means that it is going to turn on the output driver transistor, and then it starts falling, and then when the output voltage goes to around 0 volts, exceeds 0 volts, okay, when the input voltage exceeds 0 volt, the output voltage falls below -0.9 volts, which is the threshold voltage of the input transistor. So, it is going to turn off the next driver transistor of the next stage. So, basically you have a characteristics which is flat initially, then it falls and then keeps falling. Okay. So, and this the important point here is that the output voltage goes below the threshold voltage of the output transistor, and so it cuts off the output transistor. Okay. And so, again when the input voltage is -1 volt, for the next stage output voltage is going to be high. So, we see that this transistor, this structure is going to behave as a good inverter. So, we have seen the inverter structure for this particular logic and seen that it is the input output characteristics behaves as an inverter. So, if we want to make a NOR gate from this inverter, well, we follow the usual procedure, that is we have another transistor, similar transistor in parallel with the driver transistor, and so when any of these two inputs are high, okay, the output is going to be output at this point is going to be low. So, which means that it follows the NOR configuration. So, okay. Now, so we see that this is okay from the static characteristics point of view, and we have a NOR structure, but this circuit, particular circuit, has some problems. Okay, now let us look at the problems. This problem is mainly during the switching period. Okay. Now, when the output, okay, when the input, when any input, when suppose both the inputs are low and then suddenly one input goes high, then which means that the driver transistor turns on and the output voltage has to be pulled low. Okay. What happens is, in this case, when this turns on, this output goes high, the pull down action is taken place. So, this input here goes quite low, this and the pull down is going to be taken place mostly by this pull down transistor. Okay. Now, but in the other hand, on the other hand, when we look at the pull up configuration, that is when both these transistors go off, okay, all right, then what happens is the pull up has to be taken is taken care of by this load transistor. So, the load transistor must drive a current here, okay, in order to charge the output voltage, switch on the output or turn on the output transistor here, okay, the next transistor here. So, it has to supply a large current, but since the pull down transistor is always on, okay, it is a large part of the current flows into the pull down transistor, and thereby the delay is quite high, okay, because you see that this load transistor, okay, the gate to source voltage is always 0 volt. So, irrespective of the conditions, you know, this current the load current does not change, whereas for a driver transistor the gate to source voltage. So, if the input voltage goes high to 0.7 volts, there is a large current here. Okay. So, during the switching period it can provide a large current, but in this case the load transistor, because its gate to source voltage is always 0 volt. So, its current is limited, okay, and so this and a part of this current is going to flow into the pull down transistor. So, the current available for turning on the output transistor is very small. Okay. So, in order to improve this circuit, what is done is we have another configuration which is quite similar. Okay, what we have is this input part remains the same. Okay, this is the load transistor again with the gate to source shorted. So this is the inverter, and now what we have is we have another transistor here. So this output goes into the gate of this transistor, and then we have the two current diodes which are used for level shifting, and this is the pull down transistor whose gate to source is shorted, and this goes to minus VSS. Okay, and the output is taken from this point. Okay. All right. Now, if you look at these two structures here, okay, one is this structure here, okay, and then this structure here, we find that if we short these, do 2 points, that is we do not have this transistor, then we get back the original structure. Okay. Basically what we have done is we have introduced another transistor here. Okay. Now, now this transistor is called a source follower transistor, just like you have the emitter follower in a bipolar transistor, source follower, and it can be designed such that the gate to source voltage of this transistor is always 0 volts. How do you do that? Because this you see that this pull down transistor, this is the pull down transistor, this always a constant current is flowing through it, because this transistor is always in the saturation region, and the gate to source voltage is 0. So, it is in the flat part of the characteristics. So, this transistor has a constant current. Now, if we have an identical transistor here, okay, just like the pull down transistor, then what happens is this transistor, since it is identical to this and the same current is flowing through this, and this transistor also is always in saturation. That is always true, because if this is 0.7 volts here, this is the maximum value can be 0.7 volts, because it is limited by the input voltage of the next transistor. This is 0.7, this is 2.1, and if the VDD is 3 volts, so you have always a minimum of 0.9 volts across the drain as the drain to source voltage of this transistor, which ensures that this transistor goes to saturation, is always in saturation. So, if the same current is flowing, okay, through these transistors, and these are identical transistors, and if the gate to source voltage is 0 volts here, this will also be in the steady state, this will also have 0 volt gate to source. So, basically that means that the voltage at the gate and the source are the same. So, this circuit actually is going to have an identical characteristics as the previous circuit. We have a source follower, that is whatever is the gate voltage, you have a similar voltage at the source. Okay. So, from the output characteristics point of view, these are identical, but this circuit has a much better performance during the switching period. Okay. Now, let us draw the input transistor of the next stage. Okay. Now, let us see what is the difference. Now, suppose this is at 0.7 volts, which means that the output is high. Okay. Now, what happens is, suppose here this output goes high, all right, this output goes high. So, when this input goes high at this point, that is the input of this gate, it goes high, that means the output, the voltage here is pulled down to almost close to 0 volts. Okay. Now, if this is 0 volts, this is 0.7, so this point will be around 2.1 volts. So, this is close to 0 volts. So, the gate to source voltage during this period, okay, switching period, this is a very large negative voltage, which actually cuts out this source follower transistor. Okay, and since this transistor is cut off, there is no current flowing this way. So, this pull down transistor is of course on, so a current flows in this way. Okay, flows out of the input of this output transistor and discharges the input capacitance of this output transistor, and so the output voltage is going to fall. Okay. So, here there is no clash of currents. So, this pull down transistor is on, the source follower is off, and this is the full current of the pull down is used to switch off this transistor, output transistor. On the other hand, suppose this voltage is negative, say minus 1 volt, okay, that is less than the threshold voltage. So, this transistor is off. Okay. Now, suppose this also goes negative. Okay. So, this transistor is cut off. So, the input transistor is cut off suddenly, then what happens is this output voltage is going to go close to the VDD, try to approach VDD. So, now since this is minus 1 volt, so this is will be plus 0.4 volts, okay, at the source of this source follower transistor. Now, this gate voltage can rise, okay, it is not constrained as in the previous case to 0 volts. So, this gate voltage can rise and you have a 0.7 volts across the gate to source in that switching period. So, there is a large current flowing here, okay. The source follower current is going to be very large because the VGS is going to rise to 0.7 volts, and this source follower current ISF minus the I pull down, which is also going to be substantial, okay. This current is used to charge. So, the charging current is going to be ISF minus the source follower current minus the pull down current is going to charge, whereas the discharging current is just the pull down current, okay, the charging current of the output capacitance. So, now this ISF, okay, the source follower at, so in this charging case the source follower VGS is 0.7 volts. So, basically I charge will be equal to the source follower ISF at VGS is equal to 0.7 volts, because it is going to rise to 0.7 volts. Okay. So, 0.7 volts minus IPD, which remains a constant. Okay. Now, so basically this IPD, okay, is equal to I source follower at VGS is equal to 0 volts. Okay, that is how we have designed it. Okay. So, now if we design it such a way, so if we can now see that if we want I charge is equal to I discharge, I source follower VGS is equal to 0.7 volts minus I pull down is equal to I source follower VGS is equal to 0 volts. So, if we design it the transistors in such a way that the source follower current at VGS is equal to 0.7 volts minus I pull down, which is actually the source follower current at VGS is equal to 0 volt. Okay. If this is true, then is equal to the I source follower at VGS is equal to 0 volt, then the charging and discharging times can be made equal, which is not possible, which was not possible by the previous circuit. Okay. So, this circuit by introduction of the source follower here is a much better circuit compared to the previous circuit, is an improvement on that, because from the speed point of view, because during the switching period you have larger currents to charge and discharge the output capacitances. So, this circuit is called, this particular logic family is called the BFL, okay, okay, which stands for buffered FET logic. Okay, BFL or buffered FET logic. Buffered FET logic, and this is a very popular circuit for cases where you have only depletion mode devices. Okay. Of course, you can now make NOR gates by adding, just like in the previous circuit, by adding transistors in parallel to the driver transistor. So, this circuit is the buffered FET logic circuit, and the basic circuit for this logic family is the NOR gate. Okay, and with the NOR gate you can make other complicated circuits. So, this circuit again, just you have a usual NOR section followed by a level shifter with a source follower, which is used to increase or enhance the driving currents for charging and discharging the output capacitance. So, that is why this circuit is called the buffered FET logic. Okay. So, this is one of the logic families using depletion mode transistors, and it is quite popular. I will just discuss one more logic family which also uses only depletion mode transistors, which is also quite popular. Okay. This particular logic family uses Schottky diodes, okay, for logic operation. Okay. Now, and it's called the Schottky diode FET logic, or short is SDFL for short. Okay. So, Schottky diode FET logic. This logic family, as I said, also uses only depletion mode transistors, and it actually uses Schottky diodes to perform the logic operation. The advantage of using a Schottky diode is that the Schottky diode occupies much less area compared to the other devices, FETs, and thereby the area requirement is less. And so, in fact, the Schottky diode FET logic can be used for large scale integration purposes, because it requires much less area compared to the other logic families. Okay. So, basic circuit is like this. Suppose you have a circuit like this. These are all Schottky diodes. Okay. You have 3 Schottky diodes like this, and then this is for the logic operation. Then again you require level shifting, because as we said, in a depletion mode, in all depletion mode logic family, because you have to change from positive voltages to negative voltages, so that the input transistor can be cut off, you require level shifting, and again this is followed by a depletion mode device with the gate to source shorted. So, this is minus VSS. Okay. So, this is the power supply voltage. Okay. So, if you look at this section here, okay, now if you have 3 inputs A, B, C, this is nothing but an OR section. Okay. That is, when any of the input goes high, okay, the output is going to go high. So, suppose this goes high, the output is going to go, the voltage at this point is going to be high. When all the inputs are low, then the output voltage is low. Okay. Now, this is then followed by an inverter, because we require a NOR or a NAND for normal logic operation. So, as a universal logic gate. So, you have, this is the inverter. Okay. So, this is VDD. Again you have a dual power supply as in the previous case, which is inevitable in if you have depletion mode, all depletion mode structure. So, this is one of the drawbacks in fact of all depletion mode circuits. Okay. So, this is the inverter. Now, you have a logic section, this is the logic section, okay, followed by a level shifting section and followed by an inverter. Okay. Now, if you look at this, now this output voltage, okay, again if you take this as 3 volts, say this is minus 2 volt, VDD is 3 volts, VSS is minus 2 volts. Okay. Now, the output voltage, okay, can go high close to VDD, okay, when this driver transistor is off. Okay. Then the output voltage goes to say close to VDD, okay, and if the output voltage goes to VDD, okay, then what happens is if we assume we have a similar gate, this is driving a similar gate, which means that the input voltages here, okay, for this logic family can go as high as close to VDD, but as this goes close to VDD, okay, this input voltage is high, that means say 3 volt, if it is 3 volt, then this is 1, 2, 3 diode drops, this will be 0.9 volts, but this cannot exceed 0.7 volts. So, basically this 0.7, 1.4, 2.1, 2.8. So, basically this output voltage in this case is limited to 2.8 volts. Okay. All right. So, when this goes to 2.8 volts, there is the input voltage is high, and this actually the driver transistor is fully conducting. But on the other hand, okay, when this driver transistor is fully conducting, when this driver transistor is fully conducting, then what happens is this voltage goes close to 0 volt. Okay, this voltage will go close to 0 volt. Okay, say 0.3 volts. If it is 0.3 volts, okay, then the input voltage when it is 0.3 volts, if you assume that this is the input to the next stage, when the input voltage is 0.3, you have 1, 2, 3 diode drops. So, the voltage at the gate of the driver transistor is 0.3 minus 2.1 volts. So, it is minus 1.8 volts, which ensures that this driver transistor is cut off. All right. So, this driver transistor is cut off and the output voltage is going to go high. So, we see that the logic levels are compatible. Okay. That is, when the input voltage is, all the input voltages are low here, okay, it would ensure that the driver transistor here is off. So, the output is going to be high. So, when all inputs are low, the output is high. This is a NOR gate, you get, okay, and when any input goes high, the output is high. All right. So, sorry, when any input goes high, then this driver transistor is on and the output goes low. Okay. So, this output is when this goes high, this is around 0.7 volts here. So, this is going to pull down the output and the output is going to go low. So, here we have a NOR gate. Okay. So, this logic is performed using mostly Schottky diodes, and as we said, the Schottky diodes has less area. So, this is suitable for large scale integration. So, in fact, you can have a lot of variations using the Schottky diode logic FET logic family. For example, you can have OR and invert type of operations. Say for example, if you have a circuit like this, so these are the say 4 inputs. This is A, B, this is C, D, okay, and you have to follow up with a level shifting circuitry followed by the pull down transistor, okay, and here again you have another set of level shifting circuitry followed up by the pull down transistor. This is minus VSS, okay, and so this point and these points, they actually go to the input of this section. So, this is like a NAND configuration. So, here again you have the load transistor. Okay. So, if you look at this circuit now, the output is going to be low when any of these, when both these transistors, when both these driver transistors here turn on, okay, when both these transistors turn on. And when are both these transistors going to turn on? When either A or B is high and C or D is high, okay. So, the logic which is performed here is A or B and C or D invert, Okay. That is, when either A or B is high, then this particular transistor conducts, and when either C or D is high, okay, then the lower transistor here conducts. So, when both these transistors conduct, then only the lower section is going to conduct and it is going to pull the output down. Okay. So, so this particular logic function is achieved in this case. All right. Now, you can have even further complications you can also introduce. Suppose you have another section on the other side. Okay. I shall draw it like this. Okay. You have so this is the another set of depletion mode transistors, and again you have 4 more inputs, say this is one, another input here, you have 2 more inputs here, okay. Now so again similar as before, what we do is we have level shifting and pull down transistor, okay, and from here again you have another 2 diodes for level shifting followed by the pull down transistor. So these are always parts of the circuit minus VSS. Okay. Now from here you have this output going here, from here it goes here. Okay. So if you call this A, B, C, D, then this is E, F, G, H. Okay. Now what you have is, okay, in fact this is not required. All right. Now so in this particular configuration, when is the output going to go low? The output is going to go low when either this section conducts or this section conducts. Okay. When either of these 2 sections conduct, then the output then the lower part conducts and the output is going to go low. So when is any of these sections going to conduct? When both these transistors, say if this section is going to conduct when both these transistors are on, and if this section is going to conduct, okay, then both these transistors have to be on. And again, for any of these transistors to be on, any of the inputs connected to that particular transistor must go high. So then for this particular structure, the logic what we have is, what we have A plus B, A or B and C or D. Okay. So this will ensure that this particular both these transistors here conduct. For both the transistors here to conduct, you have E or F and G or H, okay, and any of these, if any of these 2 conditions are satisfied, then the output is going to go low. So you have an OR function here, and then since the output is going low when any of these conditions are satisfied, you have a bar here. So the logic which you achieve is A or B and C or D, or E or F and G or H. So you see that one can achieve very complicated logic circuits using this Schottky diode FET logic, okay, by connecting Schottky diodes basically in different configurations. Okay. So the advantage of this circuit is that again to reiterate, the advantage of this circuit is that it uses Schottky diodes mostly, and Schottky diodes occupy very much occupy less area, small area, and so they are suited for large scale integration. You can have a lot of complicated logic circuitry using small area, less area, and so it is more suited for large scale integration. Okay. Also Schottky diodes, as we have already discussed, are majority carrier devices, so they are quite high speed devices as well. Okay. The disadvantage of this particular logic family is that one major disadvantage is, if you look at this, you know, the input is always going to draw current, okay, irrespective of whether the input is high or low, because you must have these diodes on, okay, 0.7 volts, okay, for that there must be current flowing, okay. So this current has to be driven by the output of the previous gate, okay. So the output of the previous gate, okay, which is driving this gate, is always loaded, okay, by this particular gate, and of course the loading is going to be more if you have more fan outs. So the loading is going to be dependent on fan out. So all this must be taken care of while we are designing this logic circuits. So in today's class we have discussed two logic families, using depletion mode transistors. In last class we had discussed two logic families which use a combination of depletion mode and enhancement mode transistors. So of course I would like to conclude that it would the logic circuits which we discussed last class, that is which uses both depletion and enhancement mode transistors, are better in a lot of ways, in the sense that you have single power supply, okay, you have lower power dissipation because you just require 1.5 volts for the circuit operation, one single power supply at 1.5 volts. They are also quite compact in the sense, especially the direct coupled FET logic, in the sense you require very few transistors. But you have to pay for it in terms of improved technology, because you must be able to fabricate both enhancement mode and depletion mode transistors simultaneously. Okay. On the other hand, these logic families which we discussed today, which use only depletion mode transistors, they does not require so complicated technology, but you have to pay for it. You have they are not as fast as the logic circuits which we discussed last class, that is using both enhancement mode and depletion mode, and of course you have to have two power supplies and usually more number of transistors. So that way there is a trade off. So this is about FET logic family. There are of course other logic families also. In fact, there are logic families which employ only enhancement mode transistors, and some other logic families, but we will restrict our discussion to these logic families which appear to be more popular, okay, and in the FET logic family. Okay, thank you.